Now in Aspen Plus domain, let us open a new file, and that new file we open a template, and the template will be refinery template for crude fractionation. Okay, so this is the template that we will use. Now, ideally we should use metric because we have all the metric information, but if you choose metric, you won't have the required fractionation column template over here. So you use English and crude fractionation, and later you can change your data unit as and when it is required. Okay, so open the selected template. Okay, so you have opened a blank simulation, but as it is a template, it has got these component IDs. That means ideally any crude petroleum, it has these components. It has hydrogen, nitrogen, oxygen, hydrogen sulfide, carbon dioxide, methane, ethane, propane, N-butane, isobutane, then 2-methyl butane, N-pentane, N-hexane, 2-methyl pentane, N-heptane, like that, and water. And it also has crude assay. And this crude assay we have to define. Okay. So let us rename a few things so that it is easier for us. Let us rename it as methane. And then we will rename it as ethane. Rename it as propane. N-butane. This is isobutane. This is I-pentane. This is N-pentane. I think hexane is not needed. We do not have them. We can change this N-octane. We can rename it as higher hydrocarbon, because if you look at our component, we have methane, ethane, propane, ibutane, N-butane, and 2 pentanes, and we have higher hydrocarbons over here. Okay, so we do not have any identity of higher hydrocarbons. So let us put all the higher hydrocarbons in one thing, that is octane. Okay, although there is nothing specific about it, but unless we take such assumption, we will not be able to carry forward with the example problem. Okay, now go to the assay blend. Here, assay is crude. So some basic data we have to give, right? So what are the type of distillation curve? Now, we do not have ASTM D86 distillation curve, that we have to find out. We have true boiling point curve on liquid volume basis, and we have specific gravity information, right? What are the specific gravity information? We have bulk specific gravity of 0.85, so that we will write over here. And we have this data: volume percent distilled, 5, 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. So we will write over here, that is 5, 10, 20, 10, 20, 30, 40, 50, 60, 70, 80, 90, and we also have 100. And the temperature, we have to change it to centigrade. So 60, 115, 60, 115, 180, 235. So 180, 235. 295, 350. 400, 470. 545, 635, and 830. Okay, so we provide all the information of true boiling point curve. Okay, ideally this is the minimum thing we have given, but we also have some more information like the light end information, so that also we give. If we do not give, then also the simulation will work, but it will take certain assumptions which are not needed over here. If we do have those information, why not to give it? Let us give those information and expect more perfection in the simulation, right? So light end fraction is 0.00352. So we will write 0.00352 over here. And the mass fraction of these components have been given. So it is not volume fraction, it is mass fraction. First is methane. Methane is 0.015. So we write 0.015. Then ethane, it is ethane. Then propane, ibutane, n-butane. We have propane, ibutane, n-butane, then I-pentane, n-pentane, higher hydrocarbon. So it is I-pentane, n-pentane, and higher hydrocarbons. And lastly, carbon dioxide, nitrogen, and H2S. We have carbon dioxide, nitrogen, and H2S. Right. So ethane is 0.037, propane 0.253, ibutane 0.089, n-butane 0.303, I-pentane 0.097, n-pentane 0.099, higher hydrocarbon 0.095, CO2 005, 006, and 001. So 005, 006, and 001. So if you add up all of them, the sum will be 1. Okay. Now, you do not have any information about the specific gravity or API gravity over here. If you have individual information about the specific gravities of 5% distilled, 10% distilled, 20% distilled, then you can give those information over here. Okay, 5% this much, 10% this much, 20% this much. Okay. Similarly, if you have the molecular weight information, that also you can give. 5% distilled, the average molecular weight is this. 10% distilled, average molecular weight is this. So as many information that you have, okay, that you can give over here. Otherwise, leave it Aspen will calculate to the best of its abilities. Light and properties, we do not have any. In fact, we do not have any other information. So we can go to the petroleum assay characterization and we can generate the pseudo components over here. So for that, let us go to the petro characterization, and here G1 we have to choose the crude, and the crude weighting factor 1. That means we have only one assay, that is crude. Suppose we have several of such assays, like we have collected the crudes from different oil fields. So crude 1 is from oil field 1, crude 2 is from oil field 2, and so on. So we can say that crude 1 assay is 0.25 weighting factor. So 25% of crude 1 we have taken, 25% of crude 2 we have taken, and 50% of crude 3 we have taken. So this is a blend of all the crudes, and their weighting factors are 0.25, 0.25 and 0.5 respectively. Okay, so that's how we set the assay, individual assay or a blend of all the assays. Okay, and then the cuts, we choose all the cuts. That means the entire range of the temperatures. Otherwise, you can say that I want the pseudo component for the cut 20 degrees centigrade or 40 degrees centigrade or 70 degrees centigrade. Or we can say that in the range of 50 degree to 150 degree centigrade range, you find out all the pseudo components. Okay, so that's how we can set the range or list the cuts that we want. In our case, we can go for all. That means let us give this option to Aspen Plus. Let them find out what is the best way to find the pseudo components. Now let us run. Okay. Now one thing that I have forgotten to mention about the methods. Now the methods, you can see there are 3 types of methods given. That is BK10, Grayson and SRK, Redlich-Kwong-Swift. Now one more method that we can add over here, that is Chow-Cedar. Because this Chow-Cedar is quite important in petroleum refining option, so we can try out with this. Okay. Anyway, so even if you do not want Chow-Cedar, doesn't matter, you can check the result without Chow-Cedar also. What we are interested in, to find the result of the crude assay. So see the results. Here you find the results. What are the components and volume percent of assay? Methane, volume percent, weight percent and mole fraction. Okay. So these are the component breakdown, and these are the information that we have given. 5% it is 60, 10% is 115. Okay, so these are the information we have given. 60, 115, 180, 235. So there is nothing new over here. But the component breakdown we have found, it is PC66F. Now this we have not given. We have given methane, ethane, propane, all of them, but what about PC665? Pseudo component around 66 degree Fahrenheit. Pseudo component around 138 degree Fahrenheit. They have automatically divided the entire range with some typical temperature ranges, and they have named that pseudo component by using the boiling point of that cut. Now you will see the results over here. Petrocharacterization generation. So these are the pseudo component PC66F. So average normal boiling point is 65.9 degree Fahrenheit. So it has named it as pseudo component 66F. And here it is 137.732 degree Fahrenheit. So it has named it as PC138F. So likewise, it has named as per the average normal boiling point of that particular pseudo component. And there, API gravity, specific gravity, molecular weight, everything they have calculated using the Aspen's internal subroutines and all. So those are the information that you have not given, right? We have not given this information. But Aspen has calculated them with the best of their abilities based on the equations that are already set within the Aspen Plus. So that's the best pseudo component that we can generate with all the information that we have given. Okay, so that's how our petrocharacterization results are obtained. So that's how we have provided the petroleum assay characterization and we have generated the pseudo components through Aspen Plus. Now come to the simulation of atmospheric column and vacuum distillation column. Okay. Now we have to have primary distillation unit consisting of atmospheric distillation column and vacuum distillation column. First, let us work with the atmospheric distillation column and then we can attach a vacuum distillation column later in series. So for that, let us go to the simulation. There, first we have to bring this column, that is petrofrac. So we write it as atmospheric column. Okay. Now let us connect them. This is the main column feed. Okay. So let us say this is our crude feed. Or let us say crude. And we have to enter the steam also, right? Steam. So this is another one, that is steam, or we can say atmospheric or column steam. Okay. This one is vapor distillate. So we write atmospheric column vapor. This is the condenser water decant. Now we know that condenser is partial vapor liquid. So we have both vapor distillate and liquid distillate, and also we have free water. Okay, so crude has lot of free water and that free water should be decanted. So we have a free water over here and this one is the liquid distillate. So this is liquid distillate. Okay. And here we have the bottom products. We name it ATM bot. It's a bottom product. Okay. So these are the peripheral things we have to give, must. And then first let us define the crude. Crude, the flow rate is 350 tons per hour. So we have mass flow tons per hour, 350, right? And what are the temperatures and pressures? Temperature and pressure, they are 170 degrees centigrade and 2 bar. So 170 and 2 bar. So that's how we fix our crude. And then column steam temperature and pressure. Can we write it metro C bar? Okay. Yes, so it is steam, right? Steam is 400 degrees centigrade and 3 bar pressure. So it is 400 degrees centigrade and 3 bar pressure. The mass flow rate in kg per hour is 2500 kg per hour. So 2500 kg per hour. So we have set the steam also. These are all outlets. Now we have to go to the block ATM call. Now the column specification, we have 25 theoretical stages. The condenser will be partial vapor liquid. Okay, partial vapor liquid. And we do not have any reboiler, and valid phase is vapor liquid and free water. Okay, the furnace thing we will see over here. We have a distillate rate. What is the distillate rate? Distillate rate is 29,000 kg per hour. So it is 29,000 kg per hour. So configuration is set. We have to fix the stream. Now stream, the crude has to go through the furnace, right? Now you see the furnace option is not active over here, but the moment we put it on furnace, that means the crude we are setting on the furnace before the feed, then the furnace option will be open. Okay, so this is on stage 25, and steam also we provide on stage 25. The free water, ATM vapor and liquid distillate, all the distillate items are there at stage 1, and bottom product is going out through the 25th stage in liquid stage. So this is the liquid distillate, this is the vapor distillate, and this is the free water. Now go to the pressure. The pressure, condenser pressure, we have the top and bottom pressures are 1.1 and 1.3 bars respectively. So it is 1.1 bar and it is 1.3 bar, right? Then condenser temperature has been given, right? Condenser temperature is 60 degrees centigrade. So we set it over here. It is 60 degrees centigrade. And furnace, the temperature has been given, which is 355, and pressure is 2 bars. So we write it as 355 and pressure is 2 bar. Now we have to provide the information on the stripper and pump around.